Yay. Okie doke. So thank you, Ben. I wanted to do another example of oh no, these aren't even the right note. Where am I? No, just a second. Oh, what a morning. Okay, so last time we looked at the unit circle, which is a circle where the equation is x squared plus y squared equals 1. And that means that the center is at 0, 0, and that the radius is the square root of 1, which is just 1. So we've got a radius of 1. That means that we've got, since we have a center at 0, 0, we've got the x-axis values of 1 and negative 1, and the y-axis values of 1 and negative 1. But that makes the points on the x-axis 1, 0 and negative 1, 0, and the points on the y-axis 0, 1 and 0, negative 1. So for any point on the unit circle, any point x, y, we've got the property that x squared plus y squared equals 1. So let's start with a value. Let's do a different value than we did last time. Okay. Let's let x equal how about the square root of negative square root of 2 over 2? And we want to find the y values, possible y values. So how do we do that?
So your goal is to find the y values with the x equaling to negative square root 2 over 2.
Yes. So we're going to use this formula. X squared plus y squared equals 1. I really want y'all to get in the habit of writing down the formula. Even if you know it really well, it's a part of communicating. All right, so we've got x, which we know. And y, which we're looking for. And what's a good first thing to do?
Get rid of the parentheses.
Yes, very good. So the negative squared is?
That's a positive.
Good. So we can ignore that. Square root of 2 squared?
1.
2.
Wait.
Yes, 2. And 2 squared?
4.
All right. And yes, this is the same as?
1/2.
1/2. So what are we going to do with that 1/2?
Well, we know that.
Move it to the other side, making y by itself.
Okay, good. So we've got y squared is 1 minus 1/2, which is?
1/2.
1/2. That's nice. Let's see. Okay, so we've got y squared equals 1/2. Now what?
Square. Not square root.
Yes, they're good. And when we do the square root, what do we have to do?
Plus
When
or
we
minus.
take the yes, take the square root of both sides, we put in the plus or minus. Very good. So we get y equals plus or minus. And how do you take the square root of a fraction?
Square both the numerator and denominator.
Good. So we've got the square root of 1 and the square root of 2. And we can write the square root of 1 as
1.
1. Good. So we have plus or minus 1 over square root of 2. This is the best answer because it is the simplest answer. Alex makes you rationalize, so let's get in the habit of rationalizing. What do I need to do to 1 over the square root of 2 to rationalize it?
Multiply both the numerator and denominator by not negative 2, sorry. Square root of 2.
Good. And let's see, 1 times the square root of 2 is just
Square root of 2.
good. And square root of 2 times square root of 2, that's the same as square root of 2 squared, and that is
2.
The reason I say that, there are several reasons why 1 over the square root of 2 is better than square root of 2 over 2. For one thing, when you take the reciprocal of 1 over the square root of 2, what do you get?
Square root of 2 over 1.
Which is just square root of 2. When you take the reciprocal of square root of 2 over 2, you should also get square root of 2, but you get 2 over the square root of 2, and you have to rationalize, and then you have to reduce, and you end up with the square root of 2. But it's more steps. The other thing is, when we were getting this answer, we went through squaring the square root of 2 over 2. It's lots easier, I think, to square 1 over the square root of 2, just because 1 squared is simpler than 2 squared. So anyway, that enough of my rant. Most of the time in our class, I'm going to use this form when I can, because it's going to extend better. And in calculus, I'm pretty sure that Pearson, which is the software for calculus, I'm pretty sure Pearson allows that. Oh, I just got a text. Just a sec. Oh. Sorry, it's just you. Okay. Oh, I see. Yes, I'm talking to myself. I do that constant. Terrible. So now I want y'all, so the second coordinates are plus square root of 2 over 2 and minus square root of 2 over 2. And that means that we've got two y values for each x, and the same goes for the y values. So I want y'all to do this one. So this is try this one. Let y equal negative square root of 3/2. Find the possible x values that go with this y. I'm going to be here, but I'm going to do the same thing as always. I'm going to disappear.
What's up, guys?
Nothing much.
Sup?
How's your morning?
Pretty good. Pretty good.
Pretty good, pretty good. All right. Once you try this one out. Let's see. X squared plus y squared equals 1, yeah.
So the y squared would just 3/4, right?
Let's check it. So square root becomes, well, just the number in the square root, which is just 3.
Yep.
Square root 2, which is just 4. So then it becomes x squared plus 3 or 4, right?
Equals 1. So
We can
One.
try to find a value, which is x.
yeah, so x squared equals 1/4.
1/4?
Yeah, because if you subtract 3/4 from 1, you get 1/4.
I see.
And then when you do the, I say the, damn it, the root, I don't know how to
Uh-huh.
explain it.
Yeah.
It ends up as 1/4 because, well, one half. Sorry, 1/2. Yeah.
Yeah. So
Plus,
we would-
plus or minus 1/2.
yeah, plus or
Okay.
minus
Plus or
1/2.
minus 1/2. Yeah.
Since there's no other square roots in that 1/2, we should be okay.
Yeah.
Yeah.
We don't need to rationalize that one, I think.
So x could be positive 1/2 or negative 1/2.
Indeed.
Excellent, excellent. Okay, so let's go back. So we are going to wrap values onto the unit circle. So we're starting with this unit circle, but it doesn't become capital T, the unit circle, in all caps, until we apply values to its circumference. So that's what we're going to do. We're going to start at 1, 0 and wrap the positive axis onto this border, onto this circumference. But we're going to do that using the variable t and using radian values. So we're going to start here using radians, which means pi, all pi numbers. So instead of 1, 2, 3, 4, we're going to start with, for us, we're going to start with pi over 6. And pi over 6, this is nice because pi over 2 is straight up 90 degrees. Pi over pi by itself is easy. That's pi, 180. And then we think of 2 pi pretty easily. That's 360 degrees all the way around. So we think of starting at 0 and going all the way around to 2 pi. So if pi over 2 is all the way between 0 and 90 in this first quadrant, what is a third of it? How do we find a third of pi over 2?
You multiply it.
Very good. That's right. The of means multiply. And so if we multiply, we have 1/3 times pi over 2, and that is pi over 6. So anytime anyone wants you to take a third of something, you just multiply. It's kind of confusing. Okay, so we get pi over 6 for each of these regions. Well, if the first one is pi over 6, what is pi over 6 plus pi over 6?
Pi squared over 6.
We're adding, though.
One
not
third
multiplying.
pi.
So yes, we get, let's do it the long way. We get pi plus pi, so 2 pi. And the denominator stays 6, and now we can reduce it.
Pi over 3.
Yes. Does that make sense?
Ma'am?
And then, what, Sarah?
No, I just said yes, ma'am.
Oh, okay, good, good. And now we want to take half of this first quadrant. So what is half of pi over 2?
Pi over 4.
Good. And we should also be filling in the degrees. So I'm going to do that on this bigger, somewhere I have a big circle. Here we go. So we have pi over 6, pi over 4, pi over 3, and pi over 2. And now I want to fill in the degrees. So I know that pi over 2 is 90. And 0 is pretty easily 0 degrees. We always go in the counterclockwise direction. And what is a third of 90?
30.
Yeah. And so plus 30 would be,
60.
some things are easier with degrees, most things are easier with radians. So these pi measures are called radian measures. 1 radian is, it's the angle size where the arc is the same size as the radius. So 1 and 1, pretty much there. Anyway, that's not so important to us now, but radian measure is the measure involving pi. Okay, what is half of 90?
45.
Good. This is where we're going to focus right now. But I will tell you that when we move in the negative direction, we're going to call moving clockwise, moving negatively, and the values can be measured negative pi over 6, negative pi over 4, and negative pi over 3. And this would be negative pi over 2. But we're also going to get values for these angles moving positively. And that's the power of this unit circle. You can move repeated times around it, but you start to get the same values. So your angle can be huge, but it'll fit inside of this same circle. Okay, so okay. So let's look at these angles. And what we want to do is connect those angles with the point on the circumference. Because we're thinking of these as going back and forth between points and angles. We want to have a connection because the angle is actually living right here, right next to the origin. There's the angle. And here's X. And here's Y for this particular triangle. So it's a right triangle, just like we had before. We have an X and a Y, and they're connected using what now? How are they connected?
Sorry, could you ask your question one more time?
Yes. How are X and Y connected?
Would it be the hypotenuse?
Yes. What is the hypotenuse here? For the unit circle.
The degree line, like the
So-
angle line.
Is it
So
one?
how? 1, that's right. So when we're in the unit circle, this point is 1, 0. The angle associated with 1, 0 is 0 radians or 0 degrees because we're flat. So our angle is always going to be measured positively if we go counterclockwise from this line, and or negatively if we go clockwise from this line. But we're thinking of that as a direction and not a negative angle. It's still a measure. It's just a negative direction. Okay, so I want to figure out what X and Y are if this central angle, this primary angle, is pi over 6. And to do that, I'm going to copy this triangle, but I'm going to flip it. And if I drew it better, I would have landed right here. But this is also pi over 6. And 30 plus 30
60.
is 60, okay. This is length 1. What is this length?
Also 1.
So if this angle is 60 and these are both 1, these angles also have to be the same, right? For an isosceles triangle, anytime the two of the legs are the same, the corresponding angles below have to be the same.
So,
Okay, so that means we've got these two sides are both 1. That means the two base angles below them have to be the same. Yes?
yes.
And okay, so these are the same. Let's call them A. I don't know what. Okay, we've got two angles that are A's and one angle that is 60. And what is the total angles in a triangle?
180. All of them add up to 180.
That's right. So we know that 60 plus 2A, A plus A, is equal to 180. So can we figure out what A is?
Yes.
Absolutely. So help me out.
So we would, at least how I think of doing it is subtracting 60
That's
from
right.
180.
So that's 120.
Yeah.
All
And
right.
then just dividing both sides by 2.
That's not only how you think of it, that's the correct way. So I hope that's how everybody thinks of it. So we get that A is 60 also. Okay, so if A is 60, what is it called when all three angles are the same?
Equilateral triangle, I think.
Yes, and what does that mean for the sides?
All sides have to be the same.
Good, good. So now we know that this distance has to be 1. And what is half of 1?
1/2.
Yes. So we know what X is. Oh, no, pardon me, Y, because we're going in the Y direction. So we know that Y is 1/2 because we're moving positively. And we even know this one. This is negative 1/2 because it's in the, oh, no. Yes, that's right. Because it's in the negative direction. And it's on the negative Y-axis. So can we find X? Do we know how to do that?
You have to split a triangle in the middle.
Yes, that's right. So we know that X squared plus Y squared is 1 for every point on this circle. X squared plus Y squared is 1. Hey, Pierce. So we know that Y is 1/2. Can we find out the x values?
Yeah.
Yes, miss. Okay, good. So we've got x squared plus
1/2 squared, which is 1/4.
good equals 1. And now what do we do?
Subtract 1/4 from both sides.
Beautiful. And how do we subtract 1/4 from 1? Tell me the steps.
Uh,
Um,
You have to make the denominator all the same. So just multiply 1 by 4. Like 1 over 1 and then multiply by 4.
Good. So what is 1 times 4 over 4?
4
1
over
times
4.
anything is
4.
itself,
Yeah.
right?
So that's 4.
Yeah. It's 4 over 4 because that 4 over 4 is still 1. Okay, and now how do we subtract fractions?
You subtract the numerator.
Just straight across if the denominator is the same.
Beautiful. So 4 minus 1.
3.
So we get that x squared is 3/4. Now what?
Now we take the
Square root.
square root.
Yeah, square root.
Good. And when we take the square root of both sides of an equation, we have to throw in
Plus or minus.
good. I don't know why. Everybody has their own scratch to itch, but this is mine. I really, really, really love plus or minus signs when you take a square root. All right. Square root of 3 is just, can we simplify that?
Nope.
No. Square root of 4,
It's 2.
beautiful. And for x in the first quadrant, do we use a plus or a minus?
Plus.
Good. So we've got positive square root of 3 over 2 comma 1/2 for this point at pi over 6 degrees or 30 degrees. And I have a prettier version of this coming. So let's see. Let's find out. We've got 2 more, but we really only have 1 more, and I'll show you why. I want to get a clean copy. Clean copy. There we go. So we've got, let's pretend this is pi over 3. Or 60 degrees. If this is a right angle, what is this measure? So this is pi over 2 or 90. What is the third angle?
45.
Almost. So we've got 90 plus 60 plus what equals 180?
30.
Yes. 30 or pi over 6. And we are really going to push thinking of radians first. So right now we're translating into radians, but we want to be comfortable with radians first. Okay, so we've got this triangle that is 30, 60, 90, and I'm gonna still 60. And what kind of triangle is this?
Isosceles.
Again, well,
Equilateral.
it's going to end up being equilateral. Yes. So that means that all of the angles are the same, which we knew. All of the lengths are the same, and that's what we're going to use. So what is the total length for x here? The total x direction?
1.
1, and that means that half of it is going to be
1/2.
beautiful. That means that the other side, because we're on the negative x-axis, is negative 1/2. That's lovely. Now, how can we find the y that goes with that 1/2? What is it going to be? What did we just do that tells us what it's going to be?
The x squared plus y squared equals 1.
Yes, but more than that. We got 1/2. No, we got square root of 3 over 2 when we started with 1/2 before. Can we get any other answer if we start with 1/2?
No.
No, we're going to get square root of 3 over 2. And this one is still positive because we're still positive on the y-axis. So this is a really beautiful thing about the unit circle. 30 degrees is square root of 3 over 2 1/2. 60 degrees is 1/2 square root of 3 over 2. So just flipped. So there's symmetry absolutely everywhere on this circle. And that's one of the places. Now we need to find out what point goes with pi over 4. So let's see. Let's draw that. We know this is 1. We've got pi over 4, pi over 2, and let's remember, just for ease, that's 45, and this is 90. It looks like, there we go. So what is the third angle?
45.
Yeah. How did you know?
This is 45 plus 45 equals 90. And 90 plus 90 is 180.
Perfect. So we have what kind of triangle? If two of the angles are the same,
Isosceles.
isosceles, and that means that the legs in this case have to be the same. So let's call them both A, because I'm just gone on A's. We know that whatever A is, it has to be the same on both. Well, how can we find it? What do we know about these three sides?
A squared plus A squared would be 1.
Beautiful. And A squared plus A squared is?
A to the 4th.
No, we're adding. That would be
2A squared?
yes. So A squared times A squared is A to the 4th, but A squared plus A squared is 2A squared. How can we solve for A? We have to use order of operations in reverse, if that helps. That should help.
So we divide by 2 and then we take out the square root of both.
That's right. That's right. So we get that a squared is 1/2. So how do we solve that? I'm going to write it up here so that we've got a squared is 1/2.
You take the square root of both sides, but don't forget the plus or minus.
Lovely. And the square root of something squared is just itself, yes?
Yeah, itself.
Okay, square root of 1.
1
Square root of 2 is just
square
square root
root
of 2 because it doesn't have a nice square root. And this is what I was talking about before. This is my rant. 1 over square root of 2 is the natural answer for 45 degrees. And it's the easier answer for 45 degrees. But let's go ahead and rationalize this because Alex makes us. And how do we do that?
multiply both the numerator and denominator by square root of 2.
Beautiful. And so 1 times square root of 2 is just,
Square root of 2.
and square root of 2 squared.
It's 2.
Beautiful. And that means that both values of A in the first quadrant are square root of 2 over 2. And we're always going to think also 1 over square root of 2. So both coordinates of 45 degrees, both coordinates of 45 degrees are the same. That's cool. They're both 1 over root 2, or they're both root 2 over 2. So again, symmetry. The cool thing also is that in quadrant 1, X and Y are both positive. We're thinking of this as X and this as Y. What about quadrant 2? What's positive and what's negative?
X is negative, but Y is still positive.
Beautiful. Quadrant 3?
Both are
All
negative.
negative.
Beautiful. And quadrant 4?
X is positive and Y is negative.
Excellent. And that means that these points on the unit circle that I've horribly written there, let's write them more beautifully here, but they're both going to be negative. So the 30-degree one is going to be the same as 30 degrees here. So it's going to be square root of 2 1/2, but they're both going to be,
Negative.
yes. The 60-degree, and I'm just thinking of this as 60, is going to be 1/2 square root of 3 over 2. But again, they're both negative. And what about the 45 one? Those are both going to be square root of 2 over 2, square root of 2 over 2.
They're both negative, yeah.
Good. So do you see that knowing the signs of a quadrant, if you know these 3 coordinates in quadrant 1, you'll know them in all of the quadrants. So let's cheat and go to a filled in. We still have some work to do. Okay. There we go. So this is in your notes. It's page 6 in your notes. Let me see if I can zoom out. And I'll put a big one of these in the notes also. So here you can see that pi over 6, or 30 degrees, is square root of 3 over 2, 1/2. 60 is 1/2 root 3 over 2. So they're just flipped. In quadrant 2, the 60-degree angle is 2 pi over 3. And we get that from adding 60 or adding pi over 3. But now you can see that these 60-degree angles both have a denominator of 3. If we add 60 to itself one time, 30 to itself one time, we got to 60. What do we get if we add 30 another time?
90,
Yeah, and if we add 30 another time?
120.
Yeah, and that's the 60-degree angle. So we have to add 30 5 more times, 5 times total, in order to get to the first angle that doesn't reduce. So 5 pi over 6, or 150 degrees, is the 30-degree angle. So these are going to be the same, and they've got the same denominator. That's what I want you to see. If the denominator, when reduced, is 6, it's going to be a 30-degree angle. If the denominator, when reduced, is a 3, it's going to be a 60-degree value. And if the denominator, when reduced, is a 4, it's going to be a 45-degree angle. And the same thing with the pi over 2. If we get a 2 in the denominator, when it's reduced, it's either going to be top or bottom of the unit square. If we get pi when reduced, it's either going to be left or right of the unit square when you land. So all you have to do here is think even, odd, even, odd. And here we have 1 pi over 2. How many pi over 2s do we have down here? So if we add another pi over 2, where do we land? Yeah. So we've got 2 pi over 2s, which we all know is pi. We add it again, we get
3 pi over 2,
Right.
just
Good.
bottom.
good. So if we get an odd number of the form, let's see, we've got 2a plus 1 are all the odds. Every odd number for integers a, every odd number is 2a plus 1. Here we have 4 plus 1. Yes, so this is of the form 4a plus 1, and this is of the form 4a plus 3. The number out front. So a is 0, we get 3. A is 0, we get 1. every single top value will be of the form 4a plus 1. So 5, if a is 1, we'll get 5. 5, pi over 2 is going to be up top. If a is 1 down here, well, let's see, that's 7 pi over 2. If a is 2, we get 9 pi over 2. If a is 2 down here, we get 8 plus 3, 11 pi over 2. But you see how it goes. So if you know the value, you can figure out whether it's top or bottom. So, and here, if you know it even, it's going to be on the right. If you know it odd, it'll be on the left. Okay, so we've kind of got that down. That's beautiful. Let's connect some values. So I want to look at this. There's a formula for arc length. That's the distance on the top. And arc length, S, is equal to the radius times the central angle. So theta corresponds to how we're measuring theta. R is our radius. And what is our radius?
1.
One.
Yeah. So here, arc length and theta are the same. So what we're going to do is use T when we're talking about the unit circle's arc length. And that means that T and theta for the unit circle match. So the distance around and the angle, the central angle, match. And that's when everything is in radians. So this formula only works with radians. So radian measure of theta. And what that does for us, oh, these triangles are also in our notes. They're very pretty there. And I did a half or whatever job of it. But these are well-known triangles. We created them, and that's better. Here's another blank one. So we've got, that's the reason that the angle and the value of the point are often written together. So the point here, what is the point here? Not the point. What is the point on the unit circle?
1.
No,
Oh, XY?
yes. Which one is 1/2?
The Y value.
Good. And that means the other one has to be square root of 3 over 2. And that means that the 60-degree or pi over 3 angle has to be what?
1/2, comma, square root of 3 over 2.
So let's look at these sides. Which one is longer? Is the 1/2 longer or the square root of 3 over 2 longer?
Are you seeing from the point of origin?
Yeah, along the axis. So if we're measuring along the axis, is square root of 3 over 2 longer or is 1/2 longer?
The X value?
Mm-hmm. It is
The
Square root of
Pi
3
over
over
6.
2 longer, or is 1/2 longer?
Where
Along
Pi
the
over
x
6 is
axis.
longer.
Yeah, and is it a lot longer or just a little bit longer?
a little bit longer.
Well, it's like, I'm going to trace these down. So here is square root of 3 over 2. Here is 1/2. We're just looking along the x-axis. It looks quite a bit longer.
It is almost double.
Yes, and that's how I remember it. So when I'm trying to remember which one is it, is it root 3 over 2 1/2 or 1/2 root 3 over 2? I just make an angle in my head and go, which one is shorter? Oh, the y-axis is shorter for 30 degrees. Oh, okay. That must mean that y is 1/2. And up here, which one is shorter or which one is longer? It the second coordinate is longer, the first coordinate is shorter, so first one must be 1/2. I just draw them in my head and remember and figure out which one is shorter. So that's a way to remember which one to use for the pi over 6 angles or the pi over 3 angles. What do you have to remember for the pi over 4 angles? What's true about the two coordinates?
They're the same.
They're the same. And the only ones that are ever the same are,
Square root 2 over 2.
yeah. So we're going to remember it two ways. What's the other way? What's the unrationalized version?
1 over 2. So 1 over square root of 2.
Good. Because this one is way more useful. Okay, so we've got a way to remember these 3 points. Whenever we have a 1/2, the other is always root 3 over 2. Positive or negative will depend upon the quadrant. And then whenever we have 1 over root 2 or square root of 2 over 2, we know that it's a 45-degree angle or a pi over 4 angle, that the both of those are going to be the same and that it will land midway in its quadrant. So I'm trying to give y'all some ways to see that this is not hugely complicated and it's full of symmetries. Oh, I want to pause and unpause. I'm not pause. I want to